You'll probably know this from GCSE physics, but a scalar has a magnitude or size, but no direction. An example of this would be speed. On the other hand, we have vectors, which have both a magnitude and a direction, and an example of this would be velocity. Now, there's different scalars and vectors that you need to know for this topic. So let's start with the first one, which is going to be linear distance. Okay, so you'll see that it doesn't have a clear direction. It just follows the path that was taken by the car, and it's measured in meters. On the other hand, we have the vector, which is linear displacement. So it's the shortest possible line you can make between the 2 points. Okay. Another value to have a look at is going to be the angle that was taken to rotate and allow the movement, which is called angular displacement, measured in radians, not degrees. Well, it can be measured in degrees, but for this course we're going to use radians. Now, angular velocity is the radians that were used to turn divided by the time. So it's the rate of change of angular displacement, meaning angular displacement divided by time. And then we have angular acceleration, which is angular velocity divided by time, and hence radians per second, if that makes sense. Some questions in your exams will basically be calculate momentum, calculate impulse, and so all you have to do is remember the formulas. In this case for momentum it's mass times velocity. Remember to add the units in your answer as well, that's very important, don't forget the units. Yes, all you have to do is remember the formula and substitute the values that you're given in the question. Now for impulse, the unit is going to be Newton seconds because it's force times time. It's also equal to change in momentum, but I think for this course it's just force times time that you need to remember. More formulas. So linear velocity is angular velocity in radians per second that we saw before times the radius. You should know from math that the radius is half of the diameter in a circle. Okay, so it goes from the center of the circle to the circumference to the end. Then force equals mass times acceleration. Remember that acceleration is speed or velocity divided by time. And moving on, let's look at kinematics, which is the study of motion or movement. So movements can be what's called linear. They can also be curvilinear or general, which is a mix between linear and curvilinear. And let's not forget, they can also be rotational. We're going to look at rotational kinematics in the next slide. As the name suggests, angular or rotational motion or kinematics is rotating, and if you rotate a whole circle, like this gymnast, this is going to be equal to 2 times pi radians. Remember that pi is 3.14 approximately. Now, what about half a full circle? Turning half a circle? Well, that's going to be half of this, so it's 1 times 3.14 radians. And what about 2 full circles? Well, that's going to be 2 full revolutions, which is 4 times pi radians, double of this. Kinematics can also be divided into 2 types. First one being instantaneous kinematics. So this is when we're looking at huge increases in acceleration or in velocity, and using the example of a sprint, 100-meter sprint, at the start of the race, the sprinter is going to be accelerating a lot, right? And also at the end of the race when he's trying to beat everyone else to the finish line. And this, if you were shown a graph, would be calculated by the measure of the gradient. Now the opposite or the other type is average kinematics, and this is looking at overall for the whole race, what's the average velocity and the average acceleration. There's kinematics, but there's also kinetics, which are forces in movement. Now, they can be linear kinetics, or they can be not curvilinear, but angular kinetics. Resultant motion, so the ending movement, the resultant movement, depends on the following factors, which is the sum of the forces, so all the forces together that act on it, and these can be things such as gravity, contact, so you kicking a ball, friction, so the ball rolling and touching the ground constantly. These can be examples of forces, and when they sum up all together, they cause resultant motion. Let's have a look at the three laws of Newton, starting with the first law, the law of inertia. This basically states that moving objects will stay moving unless external force is applied. So if you kick a ball, it's going to keep moving until it hits another object or until it starts bouncing against the ground, so until there's friction. Or, for example, another external force would be gravity. So if you kick a ball up in the air, it's going to keep moving until gravity pulls it back down. Okay? Now, still objects stay still or stationary unless external force is applied. So if you leave a ball on the floor, it's going to stay on the floor, not moving forever until, for example, an external force like the wind or your foot kicks it away, moves it away. Second law. This law is very simple. It's simply the formula that we've seen before. Force equals mass times acceleration. So when you have more force, there's going to be more acceleration. When you have more mass, there's going to be less acceleration. So it's all based on this formula. Now looking at the last law. This law states that for every action, there's going to be a reaction, and this reaction is going to have equal force to the action and is going to act in the opposite direction. These are 6 ways in which these laws apply. Let's look at the first 4 of them. Let's start with stability. So what does it depend on? First thing we have is the center of mass, followed by the line of gravity, which goes straight under the center of mass, vertically downwards, and the base of support, okay, in this case, the feet. Now, how do you actually increase your stability based on this? Well, the larger your mass, the more stability you're going to have. The larger or wider your base of support, again, the more stability. And this is also true with the line of gravity if it is within the base of support. So we see that this person's leg right here is within the line of gravity, or it's better said if you say that the line of gravity is within his leg, his base of support. And lastly, we have that the lower the center of mass or center of gravity, the more stability as well. Summing of joint forces states that the more joints or forces that happen in the same direction, the more motion there's going to be. Makes sense. Linear motion involves a formula which is linear momentum, which equals mass times velocity. And impulse and direction also involves a formula which is that linear impulse equals force times time. We've actually already seen this formula in the video. Lastly, that impulse and direction also states that objects move the same direction as the force that was applied to it. Now's the turn for angular motion and angular momentum. Torque is the name given for rotational force, and it depends on the following factors: the size of the force, its direction, the distance from the rotational axis or pivot, and that the force must be eccentric for torque to happen. Its formula is that it equals force times perpendicular distance from pivot, or distance from the rotational axis, same thing. An example of this would be when batting a baseball bat. This would be the perpendicular distance from the pivot, which is the hand, because they're what cause the rotation, okay? Now, moment of inertia is something else you need to know, and it's how mass impacts rotation, okay? So it does so in 2 ways. First is the distribution of the mass, and the less mass distribution, the more rotation, and the less mass as well, the more rotation. Moving on to angular momentum. So this is essentially the amount of rotation induced or created by the torque from angular motion. And if we apply this to Newton's first law, we'll see that rotation continues with constant angular momentum, just like movement continues moving, until an external force, in this case unbalanced torque, also known as moment, is applied. Now, an example of this would be gravity or air resistance. When gymnasts are in the air, as we're going to see in a second, these are the main forces that are going to act on them, impacting their rotation. We can also apply this to Newton's third law, where we'll see that muscles or limbs apply a torque to the floor, which applies the same torque back. So action equals reaction with an equal force opposite direction. Now the formula for angular momentum is that moment of inertia that we've seen here times angular velocity. Now going back to the gymnasts, angular momentum is constant in the air, okay? And when a gymnast tucks in the air, he reduces his moment of inertia, so his angular velocity increases and they spin faster.